Okay, well, good morning, everyone. So this is it's actually the 5th conference. So we'll actually do the 4th one tomorrow. So this is going to be approximately an hour conference on periodic trends. Okay, so if you have a periodic table in front of you, that would be very useful. When we look at periodic trends, we're only talking about the S and the P block. We're ignoring the D and the F block for a couple of reasons. The D and the F block have very unique trends that are beyond what we need to worry about in Chem 65, and you'll deal with periodic trends of the D and the F block probably in Chem 102. So if you recall from yesterday's conference or from your reading, a cartoon of the periodic table. The periodic table roughly contains 4 blocks. We have the S block on the far left, the D block in the middle, the P block on the far right, and the F block kind of shoved down at the bottom. We said yesterday that we don't study the F block in Chem 65, so you can ignore the F block. You'll look at that in Chem 101 and 102. And for periodic trends, we can ignore the D block. So you will only be asked about periodic trends for the S and the P block. So what we're going to do, I'm going to erase this. I'm going to redraw it. I can see that Jose's joined us. Morning, Jose. If anyone, Jose or anyone else has a question, you can always use the chat function, and I'll keep looking to see if there's any questions. I'm going to erase this, and we're going to push the S and the P block together and make a rectangle. So we're artificially going to join the S and the P block together to make a rectangle. I'm going to talk about trends. Okay. The word periodic means a repeating, or any pattern that's periodic repeats over time or over space. So for example, if I walk to the Commons to get coffee every day at noon, that's a periodic event that I'm doing. People will notice, there he goes again, getting coffee. So that's a periodic event. If you notice you're driving on the freeway and every mile you notice there's a red car parked on the shoulder, that would be a periodic event. So periodic events or properties are repeating properties either over space or over time. So in chemistry, when we say periodic trends, we're talking about a property of the elements that repeats over time. When we read the periodic table, you know that we start at the top left and we end up at the bottom right. So to get from the start to the end, you have to cycle like on a helter-skelter. So you read across, you go around the back, and you appear here. Go around the back, and then you appear here. Go around the back. So you're kind of doing this. Okay. So we would say that's a periodic property with this, with this, with this. That's a periodic property with this, with this, with this. That's a periodic property with this, with this, with this, etc. That's a periodic property with this, with this, with this. So these would be periodic properties. This gives rise to the periods in the periodic table. This also gives rise to the groups in the periodic table. So for example, this would form a group. This would form a period. So these periodic properties, these repeating patterns that were observed by Dmitry Mendeleev and others, Newman and other people that noticed these things, they were just found to belong together. So like people tend to do, they associate like with like, and it was a way to arrange information. Okay, so this is what periodic means. This is where it comes from. So I don't know if there are any questions at this stage, or we should just move on. As I said, if something does come up, if you just use the chat function, I'll periodically look and see if there's a question. What I intend to do next, I'm going to erase this and we'll list the types of trends that we need to study in Chem 65. We'll define them, and then after that, we'll look at some examples. We'll explain them, and then we'll look at some examples. Okay, there we go. I'm assuming everyone can hear me and see me. If not, let me know. I'm in my office, so there's a larger whiteboard this time. So, okay. So the periodic trends, there are many periodic trends that we don't have to worry about in Chem 65. The ones that I'm going to hold you accountable for are the following. Okay, I appreciate the support. Apparently you can hear and see me. Okay, that's good. Okay, so periodic trends. We are going to be interested in ionization energy. We are going to be interested in atomic radius. We are going to be interested in electronegativity. And that is it. So these are the three and only periodic trends out of many that are out there that I'm going to hold you accountable for. Why? Because these are the three periodic trends that you would be accountable for in this class anywhere. And definitely, you know, this being a prerequisite for Chem 101, the Chem 101 professors will expect that you know this stuff, and they will then build upon it. Okay. This is academic language, and we are going to learn an academic way to think about this. But it's always good to come up with an analogy, so long as you have the discipline to know it's only an analogy. These two are the strength components. So for example, if an element has a high ionization energy, it has a high strength. If an element has a high electronegativity, it has a high strength. So electronegativity and ionization energy are two different ways of looking at the strength, the vernacular strength of the element. Atomic radius is obviously looking at the size of the element. So in Chem 65, we're interested in the size and the strength of elements in the S and P blocks of the periodic table. I'm going to erase this board, and then we'll look at exactly what these terms mean, exactly what information will be given to you in an exam, and what information you'd have to know by heart in the exam. Okay, so let's look at ionization energy first. Now, in yesterday's conference, or one of yesterday's conferences where we were looking at the fact that metals tend to lose valence electrons and become positively charged, so they become a cation, and nonmetals tend to gain valence electrons up to an 8 total, acquire a negative charge, and are called anions. Here, we're assuming everything's going to become positively charged, whether you like it or not. So we're not looking at the preference of the element to gain or lose electrons. We're going to impose the criteria that you have to lose an electron, and we're going to measure the energy needed to make that happen. So you take any element, let's call it E for element, and you take the element as a gas. So any element in the gaseous state. Why gaseous state? Because we want to eliminate any interaction between adjacent elements. So we assume that gases are truly alone. They're not influenced by each other. So it would be an isolated measurement. So any element as a gas, you want to give it ionization energy. So IE is ionization energy. And you're going to use that energy to remove an electron. So you're going to expose a positive charge. Because you've removed an electron. So this electron used to be inside the element, but you've given it energy. You've broken the interaction with the electron. You've freed the electron, and you've left a cation. Now, it would be the same equation whether it's a metal or a nonmetal. Again, we know that nonmetals don't like positive charges, but you can always rip an electron out of anything. It just depends on how much energy you're willing to put in. So we would predict that nonmetals would have a very high ionization energy because they don't want to do this. We would predict that metals have a much lower ionization energy because this is what they want to do. This is ionization energy. Notice we're only looking at one electron. Now, what if you have two valence electrons? So let's say this was one valence electron. What if you had two valence electrons? So this could be group 1, which only has one electron. This could be group 2, which has two valence electrons. Then you would have the element in the gaseous state. Let's draw a line here. You would give it, now if there's two valence electrons, you're going to have two separate chunks of ionization energy. You're going to have ionization energy 1 for the first electron. And then you can also take another electron out because you had two total. So you can have a second equation where you take the product of the first reaction and you take a second electron away with a second ionization energy. Now, these two ionization energies are not equal. The second ionization energy is always greater than the first ionization energy, and we'll see why in a second. If you take a second electron away, you're going to have a second positive charge here. So again, if you have two valence electrons, I can take both of them out. Here they are. And eventually, I'll have a positive 2 charge. But the second one is much harder to take out than the first one. So for example, if you look at calcium in group 2, we know because calcium is in group 2, it has 2 valence electrons. And we know that you'll form calcium 2 plus. But on the road to calcium 2 plus, you have to take the first one. Calcium 1 plus is much easier than the transition to calcium 2 plus. Having said that, calcium 1 plus is not stable, so you can either take 2 electrons or you take no electrons. But on the road to 2 electrons, the second one is much harder to take. But take it, you must. Let's have a quick look why the second electron is much harder to take out. Well, the first electron, you've got something that wants to lose electrons. You've got something that has no charge, so anything you do is on a neutral species. Neutral is low energy. So there is an energy because you're trying to remove an electron that's been attracted to the nucleus. The nucleus has a positive charge, so there's going to be an electrostatic attraction with the negatively charged electron that you're trying to remove. The size of that electrostatic interaction is the ionization energy. Come to take the second electron, you're trying to take it from something that's already charged. You're trying to take a negative electron from a positively charged species. A positively charged species is going to attract its negative electron as you're taking it. So as you try and take it, it's going to be caught with an electrostatic interaction that you're trying to fight against. Plus, if you're successful, you're going to expose an extra charge. The higher the charge gets, the more expensive the energetics become. So for this reason, this is much more energetically painful than the first one was. If we took something like aluminum, for example, that has 3 valence electrons, we would have IE1, IE2, and IE3. IE3 would be greater than IE2, and IE2 would be greater than IE1. Okay, again, if anyone has a question, you can just hit the chat box, and I'll have a look. Okay, so now we know what ionization energy is. Let's look at some periodic trends of ionization energy. Again, we're looking at only the S and the P block. The S and the P block. The best way to think about this is to draw a diagonal line from the bottom left to the top right. And the top right is the strong end. Bottom left is the weak end. Not the recording artist, the weak end. That's my joke for the week. Okay, so we have the weak end and the strong end. Now this is a vector, so basically the farther away you get from the tail of the arrow, the stronger you get because you're getting closer to the strong end. The closer you get to the tail of the arrow, the closer you are to the weak end, the weaker you get. So if we take this vector and we write something about it, we would say we're interested in down a group and across a period. So we would say ionization energy left to right across a period, and not just one period, but all periods. Well, if you go left to right, you're headed towards the strong end, so the ionization energy increases. If you went right to left, you would be moving away from the strong end, so it would decrease. Ionization energy going top, well, let's say going down a group, not just one group, but all groups, well, if you go down any group, you're headed towards the weekend. You go down any group, you're headed towards the weekend. So that would decrease. So you use your vector, you scribble this on your scratch paper in the Gibbs exam, and you could regurgitate the academic sentences. So ionization energy left to right across periods increases, ionization energy down groups decreases, and we're interpreting this diagonal vector here. Okay. If we superimpose a couple of elements onto this, so if you have a look at your periodic table, so let's say we have lithium here, and we have sodium, we have potassium, and then, so this is down group one, and then in the same period as sodium, we have magnesium, and then remember, this is the P block, we've thrown away the D block, so immediately in the P block, we have aluminum here. So if I asked you a question, which has a higher ionization energy, lithium, sodium, or potassium, then ionization energy for lithium, how many things are in an E? There's only 3 of them. Ionization for lithium is greater than for sodium, is greater than for potassium. Because the ionization energy is higher up the group. If I asked you which is highest for sodium, magnesium, or aluminum, then the ionization energy for aluminum is greater than that for magnesium, is greater than that for sodium. So towards the right, you're always stronger than you are on the left. If I asked you to compare lithium and magnesium, well, that's on a diagonal. So you can probably see from this periodic table, if we go diagonally, that's a tough call because you're equally far away and equally close to the head of the arrow. So I'm not going to ask you in an exam anything on a diagonal. So in the exam, there'll clearly be something closer to one end and farther away from one end. I'm not going to ask you anything on a diagonal. Okay, any questions? Feel free to send me a chat, or for those of you that are not watching this live, you can post your question in the discussion forum for the Gibbs exam, and I'll check that periodically across spring break also. Okay. All right, so I'm going to erase this, and let's look at, well, seeing as we're here, we're looking at ionization energy, which is strength. Let's look at electronegativity while we're here. So if I change this to electronegativity, then it's going to mimic the same trend as ionization energy because they're measuring the same things. If you're strong by one metric, you must be strong by all metrics. If not, your metric's wrong. So if I just replace the word ionization energy with electronegativity, we have exactly the same trend. Exactly the same. So I could put electronegativity, electronegativity, electronegativity. Exactly the same. Once again, I'm not going to ask you anything on a diagonal because it would be too close to call. So you're remembering for your exam, notice there are no numbers here yet. You don't have to memorize any numbers. You just have to know the trend, either increasing or decreasing based on location in the periodic table. You do not have to memorize any numerical values. We'll go back in a few minutes and look at exactly how electronegativity measures strength and how ionization energy measures strength and how they're different. But for completeness, let's now look at atomic radius. Okay, so atomic radius is different. And in fact, I won't spoil it. We'll look at the relationship between size and strength in a second. This is going to be atomic radius. Atomic radius, as it suggests, is size. So if you imagine an atom is approximately spherical, then you know from any math class that the radius r is the distance from the center of a circle to the outer edge of a circle. And we know that size is proportional to radius. So the larger the radius, the larger the atom, and that's the trend that's studied with atomic radius. Okay, again, if we look at the S and the P blocks, we'll have our diagonal vector again. We know this is the small end, and this is the large end. Okay, small end and large end. I'm just going to go over there and grab my coffee real quick. I grabbed the wrong one. That was yesterday's cold coffee. I guess I don't have a coffee. I've only got old coffee. Okay, never mind. Sorry about that. Okay, so we have the large end and the small end. So to put this into academic language, we would say atomic radius. The plural of radius is radii, so we just don't want to say radius. We want to say all radii. So atomic radii, the plural of radius, left to right, we're going that way, cross periods. Well, if you're going left to right, you're headed towards the small end, so the radii decrease. Atomic radii left to right across periods decrease. And this is any period in the S and the P blocks. Atomic radii down groups. You go down any group, you're going away from the small end towards the large end. So atomic radii increases. Atomic radii increase. Notice this is the opposite trend for strength. So we can see that strength is proportional to 1 over size. They have exactly the opposite relationship. If you're strong, you're small, and if you're large, you're weak. The relationship between ionization energy and electronegativity is direct. The relationship between ionization energy and electronegativity compared with atomic radius is indirect. So putting them all together, we have small and strong, large and weak. Small and strong, large and weak. Okay. Unless there's questions, I'm going to erase the board and we'll look at exactly how electronegativity and ionization energy differ. They measure the same thing from two different points of view. And it's important to get a clear idea of the difference. Okay, so let's have a look. So I'll start with an analogy. I would say that electronegativity measures pull. So think of a strongman competition. One of the activities, one of the events in a strongman competition is they have to pull things, maybe pull a truck or pull a textbook or something really big and heavy like that. That's one way to measure the strength. Ionization energy measures your grip. So if you're strong but you've got no grip, you won't be able to translate that strength into an activity. So the pulling ability of the element versus the grip of the element. What are you pulling? You're pulling a pair of electrons. So for example, if I'm an element and I have a high electronegativity, and I interact with you, I'm able to pull your electrons towards me. I have a high electronegativity, I can pull your electrons towards me. If you have a higher electronegativity than me, you'll be able to net pull my electrons towards you. If we have exactly the same electronegativity, we can pull equally, so it effectively removes the pull altogether. Ionization energy, remember, is the energy needed to rip an electron out. So the stronger your grip, the stronger the element holds on to its valence electrons, the harder it is to remove them, the higher the ionization energy. So you grip an electron. So you're either pulling electrons towards yourself or you're holding on to the electrons that you already have. Both of those would measure strength. Okay. Let's have a quick look now why the trend is what it is. So we've memorized the trend. Let's see if we can spend a few minutes explaining the trend. So let's look at a simple example to show proof of concept. Let's look at lithium and sodium. So if we can compare lithium and sodium, this is group 1. So this is down a group. If we can understand why sodium is weaker than lithium, we'll understand why ionization energy and electronegativity decrease down groups. Okay. Let's look at lithium. We can see from the periodic table, let's put the numbers in. Lithium has a value, and I'm going to round the atomic number. So lithium, if you round it, is about 7 and 3. And sodium, if you round it, is 23 and 11. So this means, and this will lead into tomorrow's conference where we look at atomic theory development. So we know that lithium has 3 protons, 3 positive charges, and it has, it also has, well, it's neutral, so it has 3 electrons. Let's say, and we're going to ignore the neutron. So we're not interested in neutrons. They don't have a charge. We need charges to explain these trends. So let's say we have 3 positive charges inside, and we have 3 inside the nucleus, and we have 3 negative charges outside the nucleus. Because all elements are neutral, so wherever this smaller number is, it's the same number of protons and electrons. Okay. But the electrons are not equal. So if you're in group 1, you have 1 valence electron. So actually, let's distinguish our electrons. We have 1 valence electron on the outside. 3 minus 1 is 2. We have 2 core electrons. So I'm going to draw a band around here. That's where I have 2 electrons. So I have 3 protons. I have 3 electrons total. It's in group 1, so I only have 1 valence electron on the outside. And I have 2 core electrons, which is this band here. Okay. Now, the ionization energy is the energy needed to pull this one away, to rip this away. So who am I fighting against? If I'm trying to take that electron away, who am I fighting against? Well, that electron is being repelled by the core electrons. That's good news for me. But ultimately, it's being attracted by the protons because opposite charges attract. Now, the distance between the center, the radius here, we know lithium is smaller than sodium. So we know that the radius is small. And I'm going to say smaller compared to this one. So it's got a smaller radius. Now, think back to Coulomb's law. Or if you've never heard of it, think forward to Coulomb's law. Coulomb's law is the law that discusses electrostatic attraction. And Coulomb's law says that the force between 2 objects, charged objects, is a constant. It's 1 over 4 pi epsilon 0, which is basically a constant. We don't really need the constant in Chem 65. Multiplied by the product of the charges over the reciprocal distance between them squared. What Coulomb's law says, if we just focus for now on r squared, where r is the radius, then the force of attraction between these charges is proportional to 1 over r squared. Because we have a small radius, r squared is going to be small, so 1 over r squared is going to be large. So we have a relatively strong interaction. It's going to be relatively hard for me to remove that electron. If you compare that with sodium, which we know is larger, we know R is larger. We have 11 protons. It's in group 1, so we only have 1 valence electron. So we have a thick band of 4 electrons. Thicker now because there's more of them. We have 10 4 electrons. 11 total. 1 valence because it's in group 1. So the only thing that changes is we get a thicker band of core electrons and more protons. So although the charge is greater, the charge is kind of neutralized because it's being shielded by a thick band of core electrons. So yes, I have more protons, but I am now attracting my core. All these negative electrons, I'm attracting those. I'm being shielded from this guy, and this is the one that we're trying to remove. Okay. There you go. My computer was being funky. Hopefully you're still there. All right. So I can take this away easier for two reasons. It's being shielded from the attractive influence of the nucleus, plus the radius is larger. As the radius gets larger, 1 over the radius gets smaller, so the force of attraction between them gets smaller. For these reasons, we see that sodium has a lower ionization energy than lithium, and this trend would continue down all groups. Okay, if there are any questions about that, I'll take them now. If not, you can put them in the Gibbs question discussion forum. But in the interest of time, we definitely need to move on in a few seconds. No question. Okay, seeing none, we'll look at why do they get stronger as you go left to right. So let's keep sodium, and let's look at aluminum. So let's just redraw that one. So let's look at aluminum. It's in the same period. So we're looking at period now. So left to right. So if we round this 2713, I don't know why I'm looking at aluminum. What happened to good old magnesium? Seemed kind of random that I went right to my aluminum. How about 2412? I saw 13, I wondered where 12 went. Okay, so let's look at magnesium. Okay, have a good class. Okay, so magnesium.
You are currently the only person in this conference.
Magnesium, we know is smaller. So we said that magnesium has 10 core electrons, 1 valence electron, and 11 protons. Magnesium has 12 protons. It's in group 2, so it has 2 valence electrons. So it likewise has 10 core electrons. You'll notice the core got thicker down a group, but the core doesn't change across a period. That's a key difference. What's changing now is not the core. Cores change down groups. Valence thickness changes across periods. Now I've got equal shielding, but what I'm shielding against is now getting bigger. So if force is proportional, let's now look at charge squared over r squared. Let's look at both of them. The charge is getting bigger. That charge and that charge, the two charges versus that and that. So my numerator is getting larger. I'm getting smaller. So my r is smaller now compared to my r, which was larger here. So my r is getting smaller. Both of these effects lead to the force of attraction increasing. So that means the valence electrons have a stronger force of attraction with the nucleus. It's much harder for me to remove them, so I experience a higher ionization energy. So this is why ionization energy increases down and increases left to right. And that explanation will explain electronegativity also. This explanation also explains radius. If you look at this part of the video again, you'll see, using this analogy, because of the force changing, it gives us a difference. So here we've used size to explain force. The reverse argument, use force to explain size, will be analogous. Okay, the only thing that remains for us to do in the last 10 minutes is look at some exam style questions. So I have prepared some. Here we go. Or I found some on the internet. So question 1 says, rank the following elements by increasing atomic radius. So you've got carbon, oxygen, aluminum, and potassium. Rank them according to increasing atomic radius. So I always recommend that you sketch the S and the P block, the space provided, and label where these elements are on the periodic table. So we know carbon is over here, oxygen is in the same period but further right, aluminum is the left and below carbon, and potassium is below aluminum and over here. Draw your vector so that you know that this is the strong and weak end, right? Strong and small end. And this is the large and weak end. Okay. So again, we've got to rank these in order of increasing atomic radius. So I want to start with the smallest one. Smallest to largest. Okay. So I have the smallest is oxygen. Then it's carbon. It's less than aluminum, which is less than potassium. The potassium is all the way down here at the large end. Let's look at another question. This one says, choose from the following pair which has the largest atomic radius. So we have Al or aluminum or boron, sodium or aluminum, sulfur or oxygen, and let's finish with bromine or chlorine. Again, you would sketch the S and the P block of your periodic table. Got your small strong end, your large weak end, and you would label where they are before you make any decisions. So boron and aluminum are right there. Sodium and aluminum are like that. Sulfur and oxygen are like this. And bromine and chlorine like that. You've got to identify which is the largest. So out of aluminum and boron, then aluminum is the largest because it's further down. Out of sodium and aluminum, sodium is the largest because it's further left. Sulfur is the largest because it's further down. And bromine is the largest because it's further down. The key is to do a sketch which you'll get credit for on the exam if you do it in your exam. Okay. Let's have a look at some other questions. This question says, rank the following in terms of increasing electronegativity, which you know is just strength. So we have sulfur, oxygen, neon, or helium. And we need to go from low electronegativity to high electronegativity. So this is not the answer, this is the question. We want the answer to follow this trend. So again, we would sketch the periodic table. We've got the strong end, we've got the weak end. Although we're not looking at the size, it's just good habit to get used to writing it so that you won't forget. It's good muscle memory. We've got sulfur and oxygen. So we have oxygen here and then sulfur here. We have helium. Now helium is way up here. It's actually not in the P block. It's actually stuck on top of the P block. It's like a chimney. And then we have neon, which is right there. Now, here's where we have to be careful. I'm sorry, I meant aluminum, not helium. Aluminum is over here. Well, I've got to rank them in this order. Neon is interesting. Neon is in group 18. That means it has 8 valence electrons. Group 18 minus the 10 d electron, the 10 d groups is 8, so it has 8 valence electrons. It's a nonmetal. We said in yesterday's conference that nonmetals want to gain electrons up to a total of 8. Well, neon already has 8, so neon doesn't want any more valence electrons. Okay, well, electronegativity is a measure of the strength of your ability to pull electrons, but we've just said that neon doesn't want to pull. So because of that reason, neon has the lowest electronegativity, although it's apparently over on the strong end. So in fact, when you think of electronegativity, you want to, at the rightmost edge, you want to stop at group 17. You actually want to ignore group 18 when you think of electronegativity. Okay, so we would have neon on the left. Then what would come next? We've got aluminum, so now we're going left to right. So aluminum is then weaker. Sulfur is below oxygen, so sulfur must be lower than oxygen. And oxygen's the strongest. I think we have time maybe for one more question. So identify from the following. So which has the greatest electronegativity? So calcium or gallium, bromine or arsenic, lithium or oxygen, barium, or strontium. Our S and our P block again. We have the small strong end. We have the large weak end. Again, with strength for ionization energy, we look at right through to group 18. Electronegativity, we stop at group 17. Okay, so we label where they are. So calcium and gallium, calcium is here, gallium is immediately here. Lithium and oxygen, lithium is way over here, oxygen is way over here. Bromine and arsenic, arsenic is way over here, bromine is way over here. And barium and strontium, strontium is over here and barium is right below it. Okay, so we've identified where everything is. We're asked which is the highest electronegativity. So gallium is closer to the strong end compared to calcium. So gallium is stronger than calcium. Bromine is closer to the right than arsenic, so bromine is stronger or higher electronegativity than arsenic. Oxygen is closer to the right compared to lithium, so oxygen is stronger than lithium. Strontium is higher than barium, so strontium is stronger than barium. Okay, so that's an example of how you'd be asked this type of periodic trend question in the exam. So hopefully that's useful. Any further questions, you can just put them on the Gibbs exam worries discussion forum on Canvas, and I'll be checking that periodically over spring break. Okay, and with that, I'm going to close the conference.